Hello and welcome to this lesson for Chemistry 20. This is the final lesson of the gases unit. So we're going to finish off the unit just looking at one more type of formula called Dalton's law of partial pressures, and then some last little bit of information on the conditions at which a gas acts as an ideal gas versus a real gas. So starting with Dalton's law of partial pressures. Dalton's law of partial pressures states that when gases do not react, they just mix together, the total pressure of the system is just found mathematically by adding each individual gas pressure together. Okay? So it is the sum of what we call the partial pressures of each individual gas. So let's look at the following example. I have a system containing 5 moles of radon and 17.5 moles of neon in a 10-liter reaction vessel at 27.0 degrees Celsius. So I have radon and I have neon. If I write down their information, my moles of radon is 5.00 moles. My moles of neon is 17.5 moles. I have a volume of 10 liters for each of them. They're in the same container, so they have a lot of the same conditions. The temperature is 300.15 Kelvin. And this temperature is also 300.15 Kelvin. I want to find the pressure of each. I'll call this P1 and I'll call this one P2. Okay? And so once I get the partial pressure of each gas, my total pressure is going to be found by adding each of those partial pressures. Okay? So we have our formula. PV equals nRT. If I want to solve for P, I need to divide both sides by V. So my pressure is going to equal nRT, 5 moles, times 8.314. I'm going to skip unit analysis in this question. Times 300.15 Kelvin, divided by a volume of 10.0 liters. Okay, I'm just going to go through quickly doing this calculation. 5 times 8.314 times 300.15 divided by 10 gives me 1,247.72 so on kilopascals for P1. And for my P2, I have 17.5 moles times 8.314 for my R times 300.15 for my Kelvin divided by my volume of 10 liters. So P2 is going to equal 17.5 times 8.314 times 300.15 divided by 10 equals 4,367.03 so on kilopascals. Now, like I said, all I need to do is add those pressures together, and that's going to give me my total pressure. So 4367 plus 1247 equals 5,614.75 so on kilopascals. Now, sig digs, we have 3 digits in all the numbers in our question, so we can only keep 3 digits. We're cutting off our decimal, so I have to move it. It'll be 5.61. I'm not cutting off a 5 or more, so it doesn't round up, times 10 to the power of 3 kilopascals would be our answer. Now, when I taught this lesson to my students, I had a very clever student who said, couldn't you just add the moles together and do the PV equals nRT calculation once? Which is true, you actually could. Because these gases are the same volume temperature in the same system, you could just add the moles together, get total moles, and then do the PV equals nRT formula once to solve for pressure. Okay? Now, why is this important? This Dalton's law of partial pressure. I do a lab with my students where we collect butane gas through the displacement of water. So we have essentially fill a graduated cylinder up with water and then release the gas out of a butane lighter into the cylinder while it's underwater. So the water comes out and is replaced with butane gas. But the problem is, in that cylinder, there's not just butane gas. There's also water vapor, okay? The amount of water vapor depends on the temperature. And in your textbook, there's a chart that tells you what the amount of water vapor there is in terms of kilopascals, so that you can solve individually for the pressure of gas by taking the total pressure, or the pressure of the atmosphere, and subtracting the partial pressure of the water vapor. Okay? So the last thing that we have to look at, like I said, is gases, whether they're acting as an ideal gas or a real gas. What does that mean? If you remember in the first lesson, we said that we can hypothetically talk about a gas in that it takes up no volume. Because the molecules are so far apart, they don't interact with each other and build up onto each other, collate together to make up any real volume. At our standard conditions, that is true. Okay, they do not take up a volume because the particles are moving very far apart. So as long as we have high temperatures and low pressures, a gas will act like an ideal gas. It will not take up a volume on its own. However, a gas will act like a real gas, deviating from the ideal gas behavior at a low temperature and a high pressure. That's when they'll act as a real gas. Okay? So I tell my students to know at which conditions a gas will act like a real gas or an ideal gas. Now, why they're acting as a real gas at low temperatures and high pressures is because the molecules are moving slowly and they're very close together. So they actually start to build up on each other and start to make up their own volume. Okay? Pressure plays a big role. High pressures play a bigger role on the effect of it, because when they're at a higher pressure, they're closer together, the intermolecular attraction starts to take over. And like I said, they build up on each other and take up a volume of their own. So when we do an ideal gas law calculation for volume, the volume would actually be a little bigger than what we predicted in our calculation, because again, the molecules combine, build up, and take up a volume of their own. Okay, so that is it for this final lesson of the gases unit for Chem 20. Thank you for watching.